Jack Jackson. In this video, we're going to be talking about the fundamental theorem of line integrals. Let's start with an exercise that I think you should probably already know how to do. Compute the integral of the function, the vector field of 3y comma sine of x over the line segment going from 1, 2 to 5, 7, and go ahead and use the standard parametrization for this. Okay? Now, you should know how to go ahead and do this one, so I'd like to ask you to do is work on this on your own, press pause and work through it, and then when you're done, come back and let's continue with the video. Press pause now. The standard parameterization of a directed line segment going from AB to CD is given by x of t is a plus delta x times t, and y of t is b plus delta y of t. Of course, where delta x means c minus a, and delta y means d minus b. This is the easiest way to get that. It will start at AB at time 0, and at time 1, it will be at CD. With our specific numbers in there, we get our position vector, r of t is 1 comma 4t, 1 plus 4t, excuse me, comma 2 plus 5t. Now, the nice thing about this particular parameterization, even though first of all, it has a nice, easy way of figuring it out, but it also has a constant speed and a constant velocity. If we take the derivative of this, we just get a constant vector 4, 5, which means as a particle is moving along here, if we think of t as being time, then the speed is the velocity is r prime, the norm of that is the speed, and we see that this is a constant speed, a constant velocity. So it's moving from one end to the other at a steady rate. Okay, the vector function for our vector field is 3y comma sine of x, and we just need to plug in our parameterization here. So in place of y, we put 2 plus 5t. In place of x, we put 1 plus 4t. Distributing here, this is 15t plus 6, and then sine of 4t plus 1. Take the dot product of that f with this r prime, and integrate with respect to t from the first to the last t, from 0 to 1. And this is the integral over that curve of f dot dr, the line integral. So it's a line integral listed over here on the left, but then we rewrite it here as this really is just a calculus 1 integral, because after you do this dot product, you see that we just have a regular calculus 1 function of a single variable. So doing the dot product, we get 4 times 15t plus 6, distributing. 4 times 15 is 60, so it's 60t, and 4 times 6 is 24 there. And then we have the 5 times the sine of 4t plus 1. This is a pretty straightforward one to do the antiderivative of. Power goes up here to 2, divide by 2, the 60 becomes a 30. The constant term 24 just picks up a factor of t. And this one you do have to do a substitution here. You let u be 4t plus 1, du is 4 dt. So you put a 4, a t, and a dt together to be the du. You balance with putting a 1/4 here. We get 5/4 there, and then we got the antiderivative sine of u is minus cosine of u. Evaluate from 0 to 1 means you just take this formula here, plug in 1 everywhere there's a t, minus parentheses everywhere there's a t, plug in 0. 1 squared is 1 times 30 is 30. 1 times 24 is 24. 4 times 1 plus 1 is 5, so this is minus 5/4 cosine of 5. That next term 0, the next term 0, and this is 1, so this is minus 5/4 cosine of 1. 30 plus 24 is 54. I'll factor out a 5/4 here and wrote this as 5/4 times parentheses cosine 1 minus cosine 5. That's probably about as simplified as I can make it. For an exact answer, and we could get a decimal approximation on our calculator, coming out to be about 54.32. All right, the next thing I want to do is say, well, what happens if we change the parameterization? We keep the curve the same, but say maybe this time instead of going from the first point to the second point, we don't do it at a steady speed, but maybe we speed up as we're going along. So see if we can work this out with a different parameterization. Here it is. So let's use this parameterization. Basically, I took the old one and just replaced t by t squared, And if you notice, t is 0, we still get 1, 2, and t is 1, we still get 5, 7, so it is starting and ending at the same place. And in fact, this still is a straight line for all the points on there. But when we take the derivative, we get 8t comma 10t, which is no longer a constant vector. Remember last time, this was a constant vector here, but this time we get something that's not a constant vector. And so we see as t increases, so does the velocity, which is what this is, and hence the speed. And so this is speeding up as it goes from one place to the other, from one end to the other. All right, with this parameterization, it's still 3y comma sine x for our vector field, but it comes out a little bit differently in terms of t, because y is 2 plus 5t squared, x is 1 plus 4t squared this time. Distribute here, we get 15t squared plus 6, and sine of 1 plus 4t squared. Take the dot product of f and dr, and that is your line integral. And so this is the dot product of the f and the r prime, and then integrate with respect to t. So once again, we're back to a Cal 1 type integral. 8t times 15t squared plus 6, let's see. T times t squared is t cubed. 8 times 15 is 120. So the first term is 120t cubed. And then we got 8t times 6 as 48t. And then, so it's first times first there, and then plus second times second. So 10t times this just picks up a coefficient in front there, 10t. Again, not too hard to take an antiderivative. The power goes up 1 to t to the 4th. Divide by the new power of 4. 120 divided by 4 is 30. 48t goes up a power to 2. Divide by the new power of 2. You get 48 divided by 2 is 24. Now this one's a little bit more, but not too much. We let u be 1 plus 4t squared. du is 8t dt. So you take the 8, the t, and the dt together, put a 1 over 8 to balance. 10 over 8 reduces to 5/4. Then you got the integral of sine of u. The antiderivative is negative cosine of u. Evaluate from 0 to 1. You can see the details worked out there. This is 30, 24, minus 5/4 cosine of 5. These two terms are 0. And that's 5/4 cosine of 1. That turns out to be, hey, same thing we got before. And this is not a coincidence. The integral always turns out to be the same if you do a different parameterization. As long as you're not changing the vector field and you're not changing the actual curve that you're tracing out, it doesn't matter how fast you trace that curve. As long as it's going in the same direction, then this will still give you this same integral. In fact, it turns out that if you just trace it in the opposite direction, you get the opposite integral. Okay, so notice that the result was the same for the last two problems. There are infinitely many different parameterizations for any specific curve. The line integral of a vector field over that curve is the same no matter which parameterization was chosen. So you can choose the easiest one you can find. For example, if it's a line, just use that standard parameterization that we talked about. Now, I'm not saying you can change the path here. We're just changing the parameterization of that path. Well, what would happen if you did change the path? Let's take a look at that. So let's do an integral here. We're going to integrate this over two different curves with the same vector field, and these two curves are going to start and stop at the same place. So here's the vector field here. F is 3y comma x squared. And our first curve is going to be over the line segment 1, 0 to negative 1, 0. All right? See if you can do that one and come back when you're done. Press pause. Well, here's the details worked out. Hopefully you did this on your own. R of t is 1 plus, well, delta x is negative 2t. So 1 minus 2t. And the y is just 0 because you start at 0 and there's no change in y, so it stays 0 the whole time. You're just tracing along a portion of the x-axis after all. And you let t run from 0 to 1 to parameterize that. Once again, this is a standard kind of parameterization for a line segment, and so this derivative should be a constant function, and sure enough, it's negative 2 comma 0. Our vector field is x plus 3y comma x squared, so replace x's by 1 minus 2t and the y's by 0. When you trace the y by 0, that 3y term goes away, so the first term is just x, which is 1 minus 2t, and the second term is 1 minus 2t quantity squared. I went ahead and squared this out, although that was actually wasted effort, because whether it's squared out or not, in the dot product down here, when we do the dot product of the f and the r prime, since that second component of r prime is 0, you're going to get 0 times this whole second component, no matter what it is going to turn out to be 0. Plus, we get the first part here times the first part here. That distributes and becomes negative 2 plus 4t. That's a super easy integral to do. You just get negative 2t and then 2t squared for your antiderivative. Evaluate from 0 to 1. You get negative 2, positive 2, 0, and 0 for the 4 terms. That adds up to 0. Now, we already discussed the fact that no matter what parameterization you may choose, as long as you're following that line segment, you're going to get the same integral. You're still going to get 0. As long as we don't change our starting and ending points, we don't change our curve, we don't change the vector field, it doesn't matter what parameterization we use, this should work out the same. Now, but what if we take a completely different path? So suppose we say go about a different path. Say, for example, suppose we take maybe let's say how about a semicircle? Okay, so same vector field, still going from 1, 0 to negative 1, 0, but let's go over a path that takes us over a semicircle centered at the origin with positive y values. Well, that's just the part of the unit circle that's in the first and second quadrants. And let's work this out. Well, if you think about this being a part of a circle, part of the unit circle, you can remember that you can parameterize that by letting x equal cosine of theta and y equals sine theta. And that parameterizes the unit circle really nicely. And we let theta go from 0 to pi. Well, I'll call it t instead of theta. But the same thing. So your r of t is cosine of t comma sine of t, t going from 0 to pi. R prime then is, the derivative of cosine t is minus sine of t, and the derivative of sine t is cosine t. Our vector function, again, this one is x plus 3y comma x squared, same as it was the last page. And we're going to substitute this new parameterization now. So I'll let cosine of t replace the x's here and here, there and there. And the y's replaced by sine t right there. So when you write that f as in terms of t, it's cosine of t plus 3 sine of t, comma, cosine squared t. So when we do our integral over that curve, f dot dr, over that particular curve, it turns out to be the integral from t going from 0 to pi, integrating with respect to t, f in terms of t dotted with this r prime here. Okay, doing that dot product, we're taking the cosine of t plus 3 sine of t and multiplying by minus sine of t. So that gives us a minus sine of t cosine t minus 3 sine squared t plus, multiply the second components, cosine squared t times cosine of t is cosine cubed of t. Notice once again that is a single variable scalar function of t. So we're back to Cal 1 again, or maybe Cal 2, because we have to do some a little bit of trig identities here. The first one's going to be set up nicely for a trig substitution. Sine square of t, you probably remember, you need to use a power reducing identity and replace that by 1/2 times 1 minus sine of 2t. You might call that a double angle or a half angle identity, or I like to call it a power reducing identity. The 1/2 times the negative 3 is the negative 3/2 here. And the cosine cubed of t, we split off one cosine of t left here. The other leaves a cosine square of t, which you can rewrite as 1 minus sine square of t. That's using one of our basic Pythagorean identity for sine and cosine. Okay, let's see what we've got here. Kind of maybe rearrange the order of the terms here, but negative 3/2 times 1 is negative 3/2. I've got a cosine of t times 1 is cosine t. I have the negative 3/2 times this negative is positive 3/2 sine of 2t. That's that term. we have the first term here, minus sine t cosine t, and the last one is the cosine t times the minus sine squared t, which is right here. So I think we got all the terms. I kind of reordered them a little bit, but there they are. They're all there. And let's go through and find an antiderivative of course, each part because we're using the sum rule. Constant function just adds a factor or multiplies a factor of t there. The antiderivative of cosine t is sine t. The antiderivative of sine of 2t, that's a substitution. U equals 2t, du is 2 dt, so this is going to put a 1/2, making this a 3/4 out front. Then I have the antiderivative of sine u is minus cosine of u. Here we let u be sine of t, du is cosine of t dt. So it's u du. And of course, you get 1/2 u squared. The minus is still out there. Similarly, over here we have u squared du. So that is minus 1/3 sine cubed of t. That's the minuses from that minus that was already there. Evaluate from 0 to pi. So you take this whole thing, plug in pi everywhere, minus, take the whole thing, plug in 0 everywhere. Don't forget you need to put parentheses around the first part and around the second part, especially for distributing this minus over here. All right, what do we get? Well, we plug in pi, we get negative 3 pi over 2. Sine of pi is 0. Cosine of 2 pi is 1, so this is negative 3/4. Sine of pi is 0 there, 0 there, 0 there. Sine of 0 is 0. Cosine of 0 is 1, so it's negative 3/4. That makes it positive 3/4. And the last two terms are 0. So that 3/4 and that minus 3/4 cancel out. All the rest are zeros, but we're left with negative 3 pi over 2. Now, wait a minute. When we went by a line segment going from here to here with that vector field, and we did the line integral, we got 0. But here, we had the same vector field. We're still going from the same point to the same point, but a different curve. This is going on a semicircle path, and we got a different line integral. So that tells you that line integrals can be, oftentimes are, dependent on what path you take. So in general, line integrals are not path independent. So notice that the last two integrals were not the same in spite of the fact that the path started and ended at the same points and they were integrating the same vector field. So in general, line integrals are not independent of path. The vector field that was given there is not a path independent field. But it turns out there are some vector fields that are such that any line integral over them is independent of path. Notice that this is a special characteristic of the field, not of the curve that you're using. So integrals in these path-independent fields depend only on the starting and ending points of the path, not on what actual path it took to get there. So if you could know that you had a path-independent field, then you should choose the easiest path which to integrate. For example, the line segment with the standard parametrization would usually be one of the easiest ones to pick. So these path-independent vector fields are also called conservative vector fields. And it turns out that if a vector field is path-independent, conservative, that's true if and only if it's a gradient field for some scalar potential function. Remember, the gradient is one way we can get the gradient of a scalar function is one way we can get a vector function. And if you come up with a function that way, it turns out to be path independent. So if the vector field is a gradient field, path independent, conservative, there is an analog of the fundamental theorem of calculus which we can also use to compute line integrals. Not only can you choose a better path, we can do something like the fundamental theorem of calculus. So part of the fundamental theorem of calculus says that if we have a function that we're integrating, if it happens to be the derivative of a known function, the antiderivative of what we start with, right, then we can compute the integral of that derivative function by evaluating its antiderivative at the endpoints of the domain of the integral and subtract. So if we can think of this as the derivative of something, some function f, then we can take that function f and just evaluate it from a to b, that is, do f of b minus f of a. Now, it turns out that we're going to do something very similar to that for line integrals, but only for ones where we have this function that we're integrating is a derivative, specifically a gradient function. A gradient is kind of a type of derivative. So if the vector field is a gradient field of some potential function f is a scalar function, then f is going to be a type of antiderivative of that gradient field that we started with. So the big F is this delta little f, or del little f. And it turns out then we could just take this potential function f, the sort of the antiderivative of sorts, and just evaluate it at the two endpoints where we stopped at minus the value where we started at. So you can see it's very similar to the fundamental theorem of calculus, hence the similar kind of name. So let's kind of illustrate that with the following example. If we start with the scalar function x plus 3xy plus 4y squared, and then take the gradient of that and let that be our function f that we want to integrate over. Let's go again from 1, 0 to negative 1, 0, and let's do it a couple of different ways. Go there directly, but use a semicircular path with positive y values. Then we'll do it again going with a linear path, and to show that those are the same thing. And then we're going to show how we can use the fundamental theorem of line integrals to get the same thing as well. So we should get the same answer 3 times here. Let's see if you can do it on your own. You should be able to do this. Try this first one and press pause when you're ready to come back. Well, here we go. We did this one earlier. If we're talking about this semicircular path, again, it's part of the unit circle in the first and second quadrants. An easy parameterization is r of t is cosine of t comma sine of t, where you let t go from 0 to pi. R prime is then negative sine of t comma cosine of t. And the function f is the gradient of this scalar function. Now remember, that gives you the partial derivative with respect to x, comma the partial derivative with respect to y. Take the derivative with respect to x, you get 1 plus 3y plus 0. So 1 plus 3y is the x component. And the y component is the derivative of this with respect to y, partial derivative. Partial derivative of the x with respect to y is 0. This term gives you a 3x, and this gives you 8y. So it's 3x plus 8y for the second one. Now, with the parameterization that we have, we're going to replace the y here by sine of t, and here, and the x by cosine of t, and that gives you the parameterization here. 1 plus 3 sine of t, comma 3 cosine of t plus 8 sine of t. Take that f function, dot product with the r prime, which is right here, and that is our line integral. Minus sine of t times this distributes, you get minus sine of t minus 3 sine squared t, plus the cosine of t distributes here, 3 cosine squared t plus 8 sine of t cosine of t. The sine square and the cosine square, unfortunately the coefficients don't match, so they don't wipe out, but we can use our power reducing identities. Replace sine square of t by 1/2 1 minus cosine of 2t, makes that a negative 3/2 there. Cosine square of t is 1/2 1 plus cosine of 2t, makes that a positive 3/2 there. Distribute the 3/2, and look what happens. You get minus 3/2 here, plus 3/2. The constant terms cancel out. So we have minus sine of t. We have 8 cosine of t, sine of t, cosine of t there. And here we have plus 3/2 cosine of 2t, plus another 3/2 cosine of 2t. That's 3 cosine of 2t. All right, now we're ready to go ahead and find antiderivatives. Antiderivative minus sine of t is cosine of t. The antiderivative here, you let u be sine of t, du is cosine of t dt. So this is 1/2 u squared. Half of the 8 is 4, and then that the u is sine of t, so it's 4 sine squared t. And over here, let u be 2t. Du is 2 dt, so you divide by 2 here. 3/2 sine of u, 3/2 sine of 2t. Evaluate from 0 to pi. You can see it there. Cosine pi is 1, sine of pi is 0, that term's also 0, that term's 1, that makes it minus. And then these are both 0, negative 1 plus negative 1 is negative 2. So we get a negative 2 when we do that, and that's actually working out with that parametrization. Now what if we change it to the let's see, that was the unit circle. What if we do it just as a straight line segment? Actually, it's quite a bit easier to work out. The vector for the position vector is 1 minus 2t comma 0, t going from 0 to 1. The derivative is then the constant vector, negative 2, 0. The gradient is still 1 plus 3y comma 3x plus 8y, but now when we plug in this, the y's are 0, so that in terms of y go away, leaving only a 1 for the x component, and the x is 1 minus 2t, times that 3 is 3 minus 6t for the y component. Then you're doing the dot product of that with the net constant vector, negative 2, 0, makes a pretty nice little function here. Negative 2 times 1 is negative 2, and 0 times this second term is 0, add that, you get negative 2, and that just picks up a t. Evaluate from 0 to 1 is negative 2, plus 0 is negative 2. Much easier that way. So it's easier to choose a better path. The easiest way, perhaps, is to look at and make use of the fundamental theorem. So the fact that we know that this is the gradient of this particular function to start with, even without finding out what the function f is, I can just take the antiderivative of this gradient, the potential function, which is actually flat out given to you in the parentheses there, x plus 3xy plus 4y squared, and evaluate that from the first point to the second point. First point is 1, 0, second is negative 1, 0. So you take the ending point and plug in negative 1 for all the x's and 0 for the y's, minus, and plug in the initial point, 1 for all the x's, 0 for the y's. And let's see, what do we get? We get negative 1 here, 0, 0, another negative 1 here, we're at negative 2, 2 more zeros, negative 2, and that's the easiest way. So we worked out the same integral 3 different ways. Twice we worked it out directly using 2 different paths, and since it's a path-independent field, remember that's a characteristic of the field, that field is a gradient field, then that allows us to choose whichever of those paths we want. But we also have this also cool result, the fundamental theorem of line integrals, that works for these path-independent gradient fields. Find a line integral of this function. Oh man, look at that kind of nasty parametrization there. But the field is 3 plus 2y, comma 2x minus 2y. Okay, and I need to have some y value, some limits on this thing. Hang on just a second. We just go from 0 to 1 again. Okay, and here's our function here. By the way, you don't always have to go to 0, 1. I just happen to be choosing that. Well, wouldn't it be nice if this was a gradient field? Let's see if we can figure that out. If it is, we should be able to find our potential function, and then we can just evaluate it at both ends. You might want to first find out what the points are at both ends. If we plug in 0, what do we get? Let's see. That's 0. That's 0. You get 1. And that's 0, that's 0, 2. So you get 1, 2. And if you plug in 1, that's 2, 0, that's 3 altogether. And here you get 3 plus 0 plus, you get 5, I think. So I think that goes from 1, 2 to 3, 5. Okay. Now let's see if we can find a potential function for this. If this is a gradient of f, I guess this is still question mark at this point, then what would have to happen? The antiderivative of the x component, of the first component, would have to be, antiderivative with respect to x, a partial antiderivative, would have to be, would be f. At the same time, f has to be the second component has to be its derivative with this antiderivative with respect to y. So this is with respect to x, this is with respect to y. All right, so we do the antiderivative with respect to x. This is 3x, this is 2xy, and then you could have a constant function, but this constant function just has to be constant with respect to x. So it could actually be a function of y. I'm just going to call it, say, a of y. And similarly, that's f has to be of that form. It has to have a term of 3x, has to have a term of 2xy, and any other terms have to only have y in them. Here I have, let's see, we're going to do the antiderivative with respect to y. So this is 2xy. This goes up to the second power divided by 2, so that's minus y squared. And the constant this time could be a function of x. Well, is this compatible? So it must have a term of 3x, must have a term of 2xy, and it must have a term of minus y squared. Well, that minus y squared is okay because that could be part of this a of y. And the 3x is okay because that could be this b of the x. The other terms do match up in both of them. And you could have plus another actual constant out here, but we can just need any potential function, not a whole family of them, so we could just might as well choose 0 for that, plus c there. All right, well, since this is actually a gradient field because we can get our hands on a potential function, then we don't have to worry about all that parametrization stuff. We can just use the fundamental theorem of line integrals. So if we want to do the line integral over that particular curve that we had of f dot dr, doesn't matter what curve it was. Actually, we can just take this potential function here, a type of antiderivative of what we started with, and then evaluate it at the endpoints. So that is, take this formula, plug in 3 for x, 5 for y, minus the same formula, plug in 1 for x, 2 for y. And let's see, that's 9, that's 30, minus 25, minus 3, minus makes that minus 4, and the 2 minuses make that plus 4. So the 4's cancel. Negative 25 and negative 3 is negative 28, plus 30 is 2, plus 9 is 11. So that shows you how you can find a potential function. We've actually looked at this in an earlier video as well. So if it has one. Now sometimes it won't work out that way. You may get down to this point here, and the terms that they have here and here aren't compatible. In other words, what's over here and what's over here you can't fix by just taking the part that just has x and plugging it in here, and the part here that just has y and plugging it in here. So they both have, one or the other has a term containing x's and y's that doesn't match. If that has a case, then it's not a gradient field. It's not going to be path independent. You're going to have to parameterize with the given path. See what happens out. Okay? But if you can get them to work out this way, you do get a potential function, and you have what you need to go ahead and apply the fundamental theorem. Now, it'd be nice if we had a little test to know before we went to this trouble of trying to find the potential function, if it's going to have one or not, and there is a way to do that. If you think of f as a function of, we'll call it m and n are the two components, that if you take the first one, the derivative with respect to y, minus the second one, derivative with respect to x, if that is 0, then it turns out that it is a gradient field. And if it's not 0, then it's not a gradient field. And so this is equivalent to the ultimate potential function that we're going to find, having to have second partial derivatives that are the same, the mixed partials. So remember, this m is the derivative of our potential function with respect to x. Then you take a derivative with respect to y. So this term right here is the f, the little f that we're looking for. It's little f x y, and this one is little f y x. So anyway, let's go back to the two vector fields that we looked at. One of these was a gradient field, and the other one wasn't. And let's just kind of test out this thing here. So in this vector field, this is one that we looked at first. If we do the partial of the first part with respect to y, you get 3. and the partial of the second part with respect to x is 2x. 3 minus 2x is not equal to 0 for all values of x and y. So this is not a gradient field, which of course bears out because earlier we saw that's the one where we got two different integrals when we use two different paths, going from the same point to the same point. But this is the one that we saw was a gradient field, okay? And you'll see that if you take the derivative of the first part with respect to y, you get 2. And the second part, you take the derivative with respect to x, you get 2. Subtract those, you get 0. And sure enough, that is identically 0 for all x's and y's. So that is a gradient field. So we kind of covered a lot of ground in this video. We talked about gradient fields, which are also known as conservative fields, are path independent. We saw that the line integrals are always parameter independent. It doesn't matter what parameterization we use, as long as we're going through the same curve, the same direction, starting and ending at the same point. Integrating over the same field works out fine. But not all vector fields are path independent, so if you take different line integrals because of same point that you're integrating for one of the other same vectors, but a different path, that may be different, that may not be the same thing. It turns out that it is the same thing. It's path independent if and only if it's a gradient field, and that happens exactly when this condition right here is satisfied.